Okay, I think we are live. Let me check for sure. Um, yeah, it looks like it. So, thank you so much, everyone, for joining. My name is Daniel Mika, and I will be talking today about Mip-NeRF and 3D representation learning. So, the goal for this stream is to really go through and understand this Mip-NeRF paper from 2021. It was a state-of-the-art solution at that time for 3D reconstruction with neural networks. And our goal here is to build a kind of understanding and background for other papers that build on top of ideas from Mip-NeRF, such as Mip-NeRF 360, and later ZIP-NeRF, and recently Neuralangelo and UniSDF that came out last week. In this way, this is a first paper in our research study series, and we will probably go through many more of these. Let me quickly refresh my camera here. And yeah, and we will be starting right now. Okay, cool. Awesome. So yeah, going through the Mip-NeRF paper, as I said. So Mip-NeRF does something called multiscale representation, and the main goal of this paper was to solve this anti-aliasing issue. But I would say this basically created a state-of-the-art at the time of like a high-quality neural representation learning. This is the main idea of this paper is basically to cast a cone and create this frustum and this representation that is not just sampling points on an array, but instead sampling these points in this visibility cone based on different pixels in the image. And this allows for this multi-resolution understanding. And we will go through the results and see how Mip-NeRF is better than the prior solution of just casting a single ray and figuring out through the middle of the pixel and figuring out values on the path. And as I said, we will talk about Mip-NeRF. In the future, we will talk about Mip-NeRF 360 by the same group of 8 authors who expand this technique to unbounded scene that is like much, it could be like any size. And then we will talk about ZIP-NeRF, which composes some ideas from Mip-NeRF and Mip-NeRF 360 with instant NGP, which is a hash grid representation method created by NVIDIA, which is very fast to train and allows for faster sampling. So this ZIP-NeRF paper is like extremely faster than any previous solutions and also has better quality. This is a comparison between Mip-NeRF and 360 and ZIP-NeRF results. So this is where we are going, and then after that we'll talk about Neuralangelo, which is more recent solution for 3D representation learning, also using hash grid from NVIDIA, also using instant NGP as backbone. And this solution is in some ways similar to ZIP-NeRF, but it's I would say parallel to it. It's not exactly building on top of ZIP-NeRF. It's doing something different, and we'll see how that works. And then we will compare all of that to UniSDF, new model from Google and ETH Zurich. That I would say probably is the state of the art currently. At least that's what they show on many benchmark datasets. And this is a very recent paper, I think published last week or 2 weeks ago, something like that. So we will talk about all of that in the upcoming live streams. And if you don't know about instant NGP, don't worry, it's not needed for today. But if you are interested to learn about instant NGP and in general about NeRFs, you can check out the video on my channel here, where we already discussed neural network, like NeRF representation learning, and the original NeRF paper and instant NGP paper. So yeah, awesome to have you here, and we'll be starting with Mip-NeRF. So this is my page here. Okay, cool. Awesome. Let's get started then. So yeah, Mip-NeRF, multiscale representation, and they are trying to solve anti-aliasing issue presented by NeRF. So let's read the abstract first. So the rendering procedure used by neural radiance fields samples a scene with a single ray per pixel and may therefore produce renderings that are excessively blurred or aliased when training or testing images observed scene content at different resolutions. So the issue is, if you train on one resolution images, let's say 512 pixels by 512 pixels, if you move the camera away or closer, you will sample the picture at the same 500 by 12 resolution, but because the picture is moved, the actual training will produce the artifacts. So we'll see that exactly later. And there were some other solutions proposed with super sampling with multiple rays per pixel, which means basically adding more rays on like a particular pixel to generate even more samples to allow for this super resolution training, where we increase the resolution input images and decrease them, and we can sample more points at different resolutions and get better results. But realistically, this is computationally very bad, because this NeRF representation, this is the standard NeRF representation here. So we have an MLP that is producing this color and density value for each point that we are sampling on the ray. And because of that, we need to sample, like if we had, let's say, 512 points, we need to go through our MLP 512 times. But then if we do multiple rays, let's say we do 20 rays, then we have 20 times as much renderings. And already rendering 512 points with this standard NeRF representation without instant NGP is like very computationally expensive. So it's important to not do that, or use instant NGP as a backbone, for example, but they are not using instant NGP here. So that's what they are saying here, like, because rendering it really requires querying a multi-layer perceptron hundreds of times, right? And they have this solution called Mip-NeRF from the Mip map idea from graphics. And this extends NeRF to represent a scene at continuously valued scale. So we'll see what they mean by that later. And they render this anti-aliased canonical frustrums instead of rays. This is the idea. These canonical frustrums will be basically these cones here that start from the pixel and go and basically correspond to all the space that can generate this one pixel from point of view of the camera. Okay. Mip-NeRF reduces objectionable aliasing artifacts and significantly improves NeRF's ability to represent fine details. Great, we love that. And it's 7% faster than NeRF and half the size. This is NeRF from the original NeRF paper, so basically this means this is 7% faster, but it's extremely slow still, because the original NeRF was extremely slow, so it's not that fast. It reduces error, great, and it is able to match the accuracy of a brute force super sampled NeRF on the multiscale dataset while being 20 times 22 times faster. So basically, as we see, this other idea is of this naive idea of like super sampling points. Yeah, very simple idea and maybe great, but in practical sense, 20 times slower. And considering this is built on top of original NeRF, this is basically extremely undoable. Like, yeah, if you want to have train these multiple NeRFs, this is like probably a few days just per one NeRF. So very bad idea. Okay, so that's when it comes to abstract. So let's go to introduction, see where we're going with it. Okay, neural volumetric representations such as NeRFs have emerged as compelling strategy for learning to represent 3D objects and scenes from images for the purpose of rendering photorealistic novel views. Yes, the NeRFs idea, as many people probably know, is that we have a set of training images and we want to create a 3D representation using these training images from for the particular scene, so that we can get a new camera position that is not in the training set and ask our 3D representation, okay, return me the image from this new camera position. And this is the task that people call novel view synthesis or novel view rendering or whatever. So this is the idea behind the NeRF. If this sounds something new to you, then I have a video on my channel that is specifically focused on explaining NeRFs, so I recommend checking out that there. Okay, let's go further. NeRF model is flawed in a manner that can cause excessive blurring and aliasing. Yes, a NeRF replaces traditional discrete sample geometry with a continuous volumetric function parameterized as a multi-layer perceptron that maps from an input 5D coordinate to 3D position and 2D viewing direction to properties of the scene, volume density, and view-dependent emittance radiance. So this is the main idea of the NeRF. So let's look at NeRF real quick. So this is NeRF, not the toy NeRF, paper, deep learning. Yes. So the main idea here, let's look at the main website, is this, right? So you input like XYZ coordinate in the space, you input viewing angle, and you get as an output RGB color at this particular pixel, and this density, which you can also like think about this density as opacity. You integrate all the values on this ray, so you need to sample all of these points on the ray, and you integrate them, and based on the color weighted by this density, you get the final color of the pixel, and you train it by making sure the final color of the pixel is the same as ground truth image, and this way you have this whole 3D representation. So then if you pick a perspective from here and the ray that goes this way, then you will just query all these points on this ray and hopefully get a good pixel value, and if you get a good pixel value, get the good image, right? So that's the idea of NeRF. So we are building on top of this idea, and this is how they explain main difference here, right? NeRF casts a single ray through that pixel and out into its volumetric representation, queries the MLP for scene properties and samples along that ray, and composite these values into a single color. So this is the main idea. While this approach works well when out training and testing images observe scene content from a roughly constant distance, so basically you want to have this in the NeRF, as we saw in this paper. Actually, let's look it back here, right? You want to have this idea here where, is there a picture like that here? Hopefully somewhere. Not necessarily. But yeah, basically what you want to have is like, you see how these two pictures are like basically similarly away from this main object in the scene, right? So this is what they mean. So they want to have, you want to have for this regular NeRF, if it is supposed to work well, you just pick some radius from the object and you try to put cameras on the same radius, best in like a dome-like shape. And when you do that, that works well, right? But then let's say you want to generate an image. You can only really generate an image in this dome, in this one like like a sphere around the object where you place all the cameras, because if you change and move the camera closer to the picture, for example, this will create these artifacts that they discuss here, because the model is not trained on this kind of data, so it doesn't generalize to this new closer in zoom ins or zoom outs kind of views, right? Yeah. So this is what they say here. When the training images observes at multiple resolutions, okay, rendering from the recovered NeRF appear excessively blurred in a close-up views and contain aliasing artifact in the distant view. So this is the issue. So even if you try to like change the resolution of the image to adjust for that, it will create blurry and aliased results. And that's likely because this network is basically doesn't have any way to explicitly distinguish between different resolution images. You just try to train it such that, okay, for this view it will generate different color, right? But if it generates different color, well, and this view also for the same space also won't generate different colors, basically what's gonna happen is the network's gonna train to generate some kind of average of these two colors. So that's likely gonna create this blurriness and this aliasing artifacts, which basically just gonna change the picture rapidly at a particular like a boundary distance, right? So let's say until here everything's good, and then you cross this small boundary created by the training data, and next step everything breaks. So that's the issue. And they say straightforward solution is to adopt the strategy used in offline ray tracing, super sampling each pixel by marching multiple rays through its footprint. But this is a prohibitively expensive for null volumetric representations such as NeRF, which require hundreds of MLP evaluations to render a single ray and several hours to reconstruct a single scene, right? So that's really bad. We don't want that. In this paper, we take inspiration from the MIP mapping approach used to prevent aliasing in computer graphics rendering pipelines. A MIP map, okay, represents a signal, typically an image or texture map. Okay, great, we love image or texture maps. Has a set of different discrete downsampling scales and selects the appropriate scale to use for a ray based on the projection of the pixel footprint onto the geometry intersected by that ray. Okay, so the idea is we have the texture of the object we are trying to model, or actually in this case in graphics just like render, and we want to understand which resolution is the best to represent the pixel based on the position of the camera. And this is known as pre-filtering, since the computational burden of anti-aliasing is shifted from the render time, as in the brute force sampling solution, to a pre-computation phase. The MIP map needs to be created once for a given texture, right? So we have this MIP map later, and then we can just use this, like, let's say like a hash table or whatever. Basically, we just use some data solution where we can just request different MIP map depending on a like dictionary or something, where we can just request different MIP map based on the perspective we have on the item, and whichever is needed, we're gonna get that. We don't have to compute this while we render, right? Which is great. Hopefully we eliminate a lot of computation. Yeah. Our solution, which we call Mip-NeRF, as in MIP map, extends NeRF to simultaneously represent the pre-filtered radiance field for a continuous space of scales. Okay. The input to Mip-NeRF is a 3D Gaussian that represents the region over which the radiance field should be integrated. Okay, let's see exactly what they mean by that. This is the input is a 3D Gaussian. Okay, cool. As illustrated in figure 1, we can then render a pre-filtered pixel by querying Mip-NeRF at intervals along a cone using Gaussians that approximate the canonical frustrums corresponding to the pixel. Okay. To encode a 3D position in its surrounding Gaussian region, we propose a new representation, an integrated positional encoding. This is a generalization of NeRF's positional encoding that allows a region of space to be compactly featurized as opposed to a single point in space. Okay, cool. So this is similar to how in the original naive pair, they like before they input this XYZ coordinate, they use this positional encoding to transform the XYZ coordinate into this high frequency representation. And they use that instead as an input to the neural network, and this allows us to get high frequency details in the picture. So this is a similar idea, but they do this in a way that will allow them to get the better representation. So we'll see if how does that work exactly, because I don't know yet, but they basically have this integrated positional encoding that also encodes the surrounding Gaussian region. So if we look at the picture 1, let's read the picture 1. So okay, NeRF samples points X along the ray, yes, that are traced from the camera center of projection through each pixel, then encodes these points with a positional encoding. So this is this function here to produce a feature, right? So this is what, and then this is the feature that is later put into the neural network to generate color and density values, right? So that's great. Let's look at the Mip-NeRF. Mip-NeRF instead reasons about 3D canonical frustum. So this basically means like all things that are behind the image to render this pixel. So this is the 3D space that's impacting this pixel here, right? Defined by a camera pixel, exactly. These canonical frustrums are then featurized with our integrated positional encoding, IPE, which is this idea that they created here, which is probably this, right? Which works by approximating the frustrum with a multivariate Gaussian. Okay, that's interesting. So we will approximate this space with a multivariate Gaussian and then computing the closed form integral expected value of this encoding over the positional encodings of the coordinates within that Gaussian. So it seems, based on this picture, each of these frustrums, these like cuts of the cone, has different multivariate Gaussian, and then when we want to get a value here, we actually don't just get like this value for a particular point, we will some kind of expected value for that Gaussian, specifically sampled from this frustrum here. So that's interesting. And they say they have closed form solution, which is great if that's the case, because closed form solution, even if it's like approximated closed form solution, that means basically this process will be much faster, because if it doesn't have closed form solution, that's probably gonna be very expensive computationally. Main idea here is to make it fast, so or faster at least. So yeah, that's good. Okay, so this is the main idea. So let's look further at what they say here. Mip-NeRF substantially improves upon the accuracy of NeRF, and its benefit is even greater in situations where scene content is observed at different resolutions. Suppose setups where the camera moves closer and farther from the scene. That's exactly what we said before. On a challenging multi-resolution benchmark, we present Mip-NeRF is able to reduce error rates relative to NeRF by 60%. That's great on average. Mip-NeRF scale-aware structure also allows us to merge the separate cores and find MLPs, use NeRF for hierarchical sampling into a single MLP. And that's very interesting. So we will see how they do that, but basically what's happening in the regular NeRF, right? When you sample the points on the NeRF, right? At first you don't know where the object is, right? So let's say you sample point here, right? You don't really care about that point because there is nothing here, right? So the density value will be very small. It's like high opacity here. So this point doesn't actually impact the color of the picture, and it shouldn't, because the object is here, that we want this point to impact the picture, right? But the issue is until you sample the point, you don't know the density, right? So you cannot just eliminate the point. So you need to compute the point and then figure out the color, right? So what they do in the original NeRF paper here, they basically do two passes of this sampling. So first they do like a uniform sampling, so they sample all the points along the rate equally. So they sample some amount of points and see where there is the most density. So here the most density will be over here, right? Where the ray crosses the part of this shovel or whatever the name of this thing is, right? So this goes through here, right? So this is the most density here. And then you sample for the second time, and you sample where you basically you weight the sampling process such that wherever you found the most density, you will sample more points there. So that's why what they call is like a hierarchical sampling here. So they call it a hierarchical sampling, and they say basically they don't need to do that here. They just have one single MLP. I'm very interested how they do that exactly, so that's cool. There are ways to do it. We already saw that in different papers where they do that, but I assume this is related to basically kind of like maybe figuring out precisely what's the intensity of each of these Gaussians, because we can see that for some reason this Gaussian is much darker than this one or this one, so this might correspond to how much density we expect to have in this particular Gaussian based on all the training that we had done since beginning of the training of this Mip-NeRF, right? So that might be good. Okay, so let's go further. So now we're gonna go into related work sections, which basically discusses all the NeRFs and all the different papers they're gonna reference here. So let's read it through quickly and move forward. So they extend NeRF, of course. Cool. They review 3D representation used by computer graphics with synthesis, including recent introduced continuous neural representations such as NeRF. We focus on sampling and aliasing. Okay, anti-aliasing in rendering. Sampling and aliasing are fundamental issues that have been extensively studied through development of rendering algorithms in computer graphics. Reducing aliasing artifacts, anti-aliasing is typically done via either supersampling or pre-filtering. Supersampling-based techniques cast multiple ray per pixel while rendering in order to sample closer to the Nyquist frequency. Honestly, I don't know what that is, but that's probably a very important idea in computer graphics, so that's great. And this is an effective strategy to reduce aliasing, but it is expensive as runtime generally scales linearly with the supersampling rate. Supersampling is therefore typically used only in offline rendering contexts. Instead of sampling more rays to match the Nyquist frequency, pre-filtering based techniques use low-pass filtered versions of the scene content to decrease the Nyquist frequency required to render the scene without aliasing. Okay. Pre-filtering techniques are better suited for real-time rendering because filtered versions of scenes content can be pre-computed ahead of time and the correct scale can be used at render time depending on the target sampling rate. In the context of rendering, pre-filtering can be thought of as tracing a cone instead of a ray through each pixel. Wherever the cone intersects a scene content, a pre-computed multiscale representation of the scene content such as sparse voxel octree or a mipmap is required at the scale corresponding to the cone's footprint. So basically, as we have this here, if we were just doing like a regular graphics rendering, probably what they would do, have this cone, and for each of these like discrete kind of portions of the cone, we will render a texture at different resolution, right? Depending on how far it is from us. So on the close, we will get like a high resolution, at further low resolution, and this way we will remove these anti-aliasing issues and adjust for like how far the camera is to have like a corresponding resolution correctly. Let's look further. Okay. Our work takes inspiration from this line of work in graphics and presents a multiscale scene representation for NeRF. Our strategy differs from multiscale representations using traditional graphics pipelines in two crucial ways. First, we cannot pre-compute the multiscale representation because the scenic geometry is not known ahead of time in our problem setting. Exactly. So this is the idea I discussed already for this hierarchical sampling, right? If we knew exactly where to compute the points, because we will knew, this is like a cup or this is a machine or whatever, and it looks like this. If we know how it looks, right, then we can just like pre-compute all the pictures that we're gonna train on it, and we just have to like figure out the color then, because we exactly can sample at the wherever the density is 1, right? Wherever the density is high, we just sample there because we know the density, but we don't know the density. We also model the density in our solution, right? So this is what they say when they say we don't know ahead of time the scene geometry, right? Because geometry in our case is represented by this density here. So what they do, we are recovering a model of the scene using computer vision, not rendering a predefined CGI asset. Exactly. Mip-NeRF therefore must learn a pre-filtered representation of the scene during training. Yes, so in our case, we will learn these different representations while we optimize the neural network with the training data. Second, our notion of scale is continuous instead of discrete. Instead of representing the scene using multiple copies at a fixed number of scales, like a MIP map. Yes, so this is the idea, right? So as I said, you just divide this code into different scales. This is similar to LOD in graphics and things like that. You have like different levels of details for different assets at different lengths, and you have different quality of images, right, to texture them. Instead, here we have a line in the volumetric space, right? So we need to be able to generate this sample the points at continuous space, and this model can be queried at arbitrary scales. So that's why they say like we cannot have like a model that's like, let's say, generates images and then assigns them different spaces, because there are too many of these options, right? Much better idea here is to just allow for the continuous representation, where you can like basically neural network can like create internal representation for each space, all possible spaces at the same time, right? Especially if the training data is at varying resolution and varying length and from the object, then that's very important, because if you want to be able to sample the new camera view at any resolution and length from the picture, then that means basically that you need to also have this continuous representation. Okay, let's go further. So scene representations for view synthesis. Various scene representations have been proposed for the task of view synthesis, using observed image of a scene to recover a representation that supports rendering novel photorealistic images of the scene from unobserved camera viewpoints. So this is how they basically discuss this idea of novel view synthesis. When images of the scenes are captured densely, light field interpolation techniques can be used to render novel views without reconstructing an intermediate representation of the scene. Issues related to sampling aliasing have been thoroughly studied within this setting. Methods that synthesize novel views from sparsely captured images typically reconstruct explicit representation of a scene 3D geometry and appearance. Many classic view synthesis algorithms use mesh-based representations along with either diffuse or view-dependent textures. Mesh-based representations can be stored efficiently and are naturally compatible with existing graphics rendering pipelines. However, using gradient-based methods to optimize mesh geometry and topology is typically difficult due to discontinuous local minima. Basically, training any kind of mesh generation is usually very difficult, and that is because mesh is basically the graph structure in 3D that has like nodes and edges between the nodes, and mostly the nodes are connected in the triangles usually. That basically creates this 3D shape in the space. But the issue is you have to either create new nodes or destroy nodes sometimes to create a new representation, new shape, right? And also the topology is not necessarily continuous. You might have like a mesh and then an empty space and another mesh, and that might be the same object, but like there is like a discontinuity there. So things like that are extremely difficult to generate with the neural network, because you have to have a lot of like heuristics and other things that could solve that issues. So that's why the neural networks and like NeRFs work much better, and that's they're gonna say here probably. Volumetric representations can therefore become increasingly popular for view synthesis. Exactly. Early approaches are color voxel grids using observed images, and more recent volumetric approaches use gradient-based learning to train deep networks to predict voxel grid representations of scenes. Discrete voxel-based representations. Okay, blah blah blah. Coordinate-based neural representation. So this is exactly like a NeRF basically. Represents 3D scene as continuous function parameterized by MLPs that map from a local 3D coordinate to properties of the scene at that location. Some recent methods use coordinate-based neural representation to model scenes as implicit surfaces, but the majority of recent view synthesis methods are based on the volumetric NeRF representation. NeRF has inspired many subsequent works that extend its continuous neural parametric representation for generative modeling, dynamic scenes, non-rigidly deforming objects, photo, blah blah blah, and other applications. So yeah, NeRFs, widely popular, successful, great. Little attention has been paid to the issue of sampling and aliasing with the context of view synthesis using coordinate-based neural representations. Discrete representations used for view synthesis, such as polygon meshes and voxel grids, can be efficiently rendered without aliasing using traditional multiscale pre-filtering approaches, such as MIP maps and octaves. However, coordinate-based neural representations for view synthesis can currently only be anti-aliased using supersampling. So this is the naive idea, which breaks the already slow rendering procedure. Recent work by someone proposes a multiscale representation based on sparse voxel octaves for continuous neural representations of implicit surfaces. Okay, but their approach requires that the scene geometry be known as prior. Okay, so that doesn't work. It's basically great approach, but only if you know the sigma, and it's pretty good. So as soon as you don't know the geometry, it doesn't work. As opposed to our view synthesis setting, where the only inputs are observed images. So this is like a standard setting for NeRF. They address this problem, enabling efficient rendering of anti-aliased images during both training and testing. Okay, so now they will discuss the NeRF and how the NeRF works. So we will have a short review of the NeRF, and then we go into the method of their paper. So let's see, how do they describe NeRF? NeRF uses the weights of multi-layer perceptron to represent a scene as a continuous volumetric field to particles that block and emit light. Yeah, so this is the idea where basically you have a 3D space and you have a particle at different points, and if their density is there, so the particle exists there really, and then it will emit some light into the camera because some light is on this particle, and it's creating a color, right? So NeRF renders each pixel of a camera as follows. We have our air ray as RT, and this is basically the always the center of camera, and the TD is the this is the where on the ray in the direction D is the particular point that we want to render. And we have like a sampling strategy that is used to determine a vector of sorted distances t between the camera's predefined near and far planes. So this is a bit different than regular NeRF, I think. Yeah. And t is the distance from the camera to the point we are rendering, right? So that's cool. Okay. For each distance tk in t, we compute its corresponding 3D position along the ray with this function, and then transform each position using a positional encoding. This is from the regular NeRF paper. You just put this x into sine and cosine function and compute this vector, and this is your input to the neural network. Instead of just inputting this xyz vector, you input this bigger vector. And this is simply the concatenation of sines and cosines of each dimension of the 3D position x scaled by the powers 2 from 1 to 2l minus 1, where l is a hyperparameter. So we will see what l they use, but probably something along like 8. The fidelity of NeRF depends critically on the use of positional encoding, as it allows the MLP parameterizer to parameterizing the scene to behave as an interpolation function. Yeah, interpolation function, where L determines the bandwidth of the interpolation kernel. So this is what they found out why this works better. So basically, if we just use the XYZ coordinates naively, this works much worse. And if we use this transformation for the input, it might have much easier time interpolating into the 3D space from these pre-computed parameters. And the positional encoding of visual position is provided as an input to MLP parameterized by weights, which outputs a density and RGB color C. So this is our MLP here, right? And it's, as I said, output for each point K. It outputs density and color at that point. And this MLP also takes view direction as input, which is omitted for notation simplicity, but as you remember, it also takes this as an input, so they also do that here. These estimated densities and colors are used to approximate value rendering integral using numerical quadrature. So this is the idea. TK is basically the density that we observed from the beginning of integration to point K, to the iteration K. So this we sum of all K primes that are below the K from the camera, and we just calculate the density collected until the ray. So if there is a lot of density, then the next should have less impact, right? And then we basically have this term here, which is saying how much density we have at this part, difference between these 2 points that we sample, and we multiply by the color that we had sampled. So this is how we get our final color for the pixel. Exactly. Blah blah. We train it with set of observed images with known camera poses. We minimize the sum of square differences between all input pixel values and the all predicted pixel values using gradient descent. So this is a standard L2 loss for NeRFs. And to improve sample efficiency, NeRF trains 2 separate MLPs, one coarse and one fine, with different parameters, where C star is the observed pixel color taken from the input image, and R is the set of all pixel rays across all images. Some people construct TC by sampling 64 evenly spaced random T values with stratified sampling. Decompositing weights produce the coarse model, are then taken as piecewise constant PDF describing the distribution of visible scene content, and 128 new T values are drawn from the PDF using inverse transform sampling to produce TF. The union of these 192 values are then sorted and passed to the fine MLP to produce final predicted pixel color. Yeah, so we can see the idea is we use the one network to use evenly spaced random T values, and we have 64 of them, and then based how the density is there created, so this is the term from our calculation here, right? So this is the term basically of how much we should care about color at that particular point. So we use that as a weight, and then we use inverse transform, and we create a PDF function that lets us, and we sample from this new PDF that basically lets us to sample points where the weight is high, right? So there will be more points where the weight is high, and we have 128, and we take the 64 plus 128 values, and we use this last network to produce the final predicted color. So this is the idea, and this is our loss function, very typical loss function here. Okay, so let's go to the method of this particular paper. Let me put light on. Okay. Yeah, so they talk about how point sampling makes it vulnerable to issues related to sampling and aliasing. And the color is the integration of all incoming radius within the pixel frustum. NeRF casts a single infinitely small narrow ray per pixel, resulting in aliasing. Mip-NeRF resolves this issue by casting a cone from each pixel. Instead of performing point sampling along each ray, we divide the cone being cast into a series of canonical frustrums. Cones cut perpendicular to their axis. So these are the frustrums they talk about. They mean one of these kind of like cuts of the cone at different levels. Okay, so they have these canonical frustrums. And instead of constructing positional encoding features from an infinitesimally small point in space, which is this particular sample point, we construct integrated positional encoding. This is the main idea here. Representation of the volume covered by each frustrum. So they have like a one representation per each of these kind of cutted cones, that's why probably the expected value is here, which is great. Okay. These changes allow the MLP to reason about the size and shape of each canonical frustrum instead of just its centroid. Yeah, so instead of just taking this one point in this space, we reason about how big is the Gaussian that we're gonna use to estimate that whole space that we're gonna use to create the color of the pixel. Yeah, ambiguity resulting from NeRF's insensitivity to scale and Mip-NeRF's solution to this problem are visualized in figure 3. We will go there. This use of canonical frustrum IP features also allows us to reduce NeRF two separate cores and fine MLPs into a single multiscale MLP, which increases training and evaluation speed, reduces model size by 50%. Great, loving that. What's the figure 3? Okay, let's see here. NeRF works by extracting point sample positional encoding features, as shown here as dots, along each pixel array. These point sample features ignore the shape and size of the volume viewed by each ray, so the two different cameras images the same position at different scales and might produce the same ambiguous point sample features. So two different cameras imaging the same position at different scales may produce same ambiguous point sampled feature, thereby significantly degrading its performance. In contrast, Mip-NeRF casts cones instead of rays and explicitly models the volume of each sample canonical frustrum, thus resolving this ambiguity. Okay, so the whole point of this idea here, of this picture, is you see how, if you look at the dots, this is how the regular NeRF works, and then if you look at this like cone-like trapezoids or whatever here, that represents basically like a 2D cut of these cones that we have in 3D, right? So the idea here is that if you have a NeRF representation, this red thing will produce exactly the same values under the NeRF. Because you just have a point, you put it through the encoding, and no matter how far it is from the camera, it will have exactly the same representation that you put into MLP. So basically this point is generating the same thing for this camera and this camera. And that from one perspective might be great because you want to have like one point to be consistent with no matter how you look at it. But actually you want this point to have different resolution, because for this camera this point is very close, and for this camera this point is much further. You see, for this camera this is a second point, and for this camera is 1, 2, third point, and these points are sampled much further. So what they do, because they don't just train it for like representing this point, it trains to represent this whole like a cone-like thing in 3D, right? The feature is gonna represent this cone-like thing. So first of all, it's gonna represent this space here on the blue, right? that is not represented in the space that is like yellow, right? Second of all, this blue thing is much smaller than the yellow thing, right? So because of these differences, right, you have a very different input for the neural network. And this way the neural network can really understand, okay, I'm looking at this small cone and it's looking exactly like that. So I should generate some specific values, and if I'm looking at this cone that is much bigger, I should generate something different. So that's how they say that this is like scale insensitive, because it doesn't, like the regular NeRF is scale insensitive because it doesn't care where the point is compared to the camera, and their solution will be sensitive to the scale because it will create different features depending if the cone is here, or depending even for the same point that is here, right? It will generate different features for this kind of length from the camera and different features for this length from the camera, right? So this allows us to differentiate between what should I render for the close-up camera and what should I render for the far-away camera. This is what we want, right? So that's what they mean by explicitly models the volume of which sample canonical frustum, shown here as trapezoids, resolving the ambiguity, right? So the explicitly they have for each of these frustrums, they have different features. Okay, let's go. Cone tracing and positional encoding. Here we describe Mip-NeRF's rendering and featureization procedure in which we cast a cone and featureize canonical frustrum along that cone. As in NeRF, images in Mip-NeRF are rendered 1 pixel at a time, so we can describe our procedure in terms of an individual pixel of interest being rendered, right. For that pixel, we cast a cone from the camera's center of projection O along the direction D that passes through the pixel's center. Yeah, that's like as usual. The apex of that cone lies at O, and the radius of that cone at the image plane O plus D is parameterized as R. So this is this is O, and this is this, or even they marked it here, right? So this is the radius of this cone here, right? So we see that there are some small spaces here because this is like a circle in the square, right? But basically this is the radius of the upper side of the cone here, right? So we don't model this part because we don't have data here. We have picture at this length from the camera, so this is where we get the radius from. Okay, let's read further. We set this value to the width of the pixel in word coordinates scaled by this magical number. This is just from geometry, I think, of some kind. I'm not gonna think about it too hard, but that's probably what makes it a cone, which yields a cone whose section on the image plane has a variance I in X and Y that matches the variance of the pixel's footprint. The set of positions X that lie within the canonical frustrum between the two values of T0, T1 is, okay, let's understand that. So T0, T1 is a different level. So this is like T0 and this is T1, right? So this is like a particular cut of the cone at this particular scale. Yeah. So this is, what is this? This is an indicator function, okay? Cool. F of x equals 1 if x is within the canonical frustrum defined by this thing. Okay, so we check if the T0 is less than dt x minus O. Yeah, so we check basically if the dt that we're inputting here is in this range of T0 to T1, and we also check if it's in the cone, basically, if I understand correctly. Yeah, so this checks the radius and this checks the edges of the cone. If we fit in the cone, then we get 1. Great. Ideally, this featureized representation should be of a similar form to the positional encoding features used in NeRF. Show that original NeRF paper showed that this feature representation is critical to NeRF's success. There are many viable approaches for this. They also have some discussion we're gonna review later. great. But simplest and most effective solution we found was to simply compute the expected positional encoding of all coordinates that lie within the canonical frustum. That's really cool. That's really cool. So the idea is, how do you basically approximate one value for the whole cone? Well, basically you assume you're gonna have some expected, this is like a expected value. You would sample all the points. What would be the result, right? What would be the integrated result? What would be the expected value for all these sampled points, right? So this way you have one number, right? So you want expected value, so that's why probably they use this Gaussian representation for this, so that you have easier time calculating the expected value of the cone instead of if you had like actual this geometrical shape in 3D, right? So let's see how they do that exactly. Yeah, so this is the this is typical function times the geometry divided by the volumetric size of the space. So this is the expected value. Yeah, it is, however, unclear how such feature could be computed efficiently, as the integral in the numerator has no closed form solution, right? Because this is some random function for the cone. We therefore approximate the canonical frustum with a multivariate Gaussian exactly, which allows for an efficient approximation to the desired feature, which we will call an integrated positional encoding, right? So they just gonna pretend that instead of having like a cone, we're gonna have a Gaussian multivariate, like 3D Gaussian here, and this is gonna be great for sampling and calculating the expectation of that. To approximate the canonical frustum with multivariate Gaussian, we must compute the mean and covariance of this function. Because each canonical frustum is assumed to be circular, and because canonical frustrums are symmetric around the axis of the cone, such a Gaussian is fully characterized by 3 values in addition to O and D, and the mean distance along the ray UT, the variance along the ray, and the variance perpendicular to the ray, right? Yeah, so the idea is, the only thing we need to figure out is where is UT on the ray, how much variance is here, how much variance is here, right, along the ray, and how much variance is perpendicular to the ray, and then you can like sample from this, and in this case not sample, we could just calculate the expectation, right? So this will produce for us all the information we need. So that's good. What's next? So this is calculated with these equations. So these are parameterized with respect to midpoint TU, which is in between T0 and T1, and half width T1 minus T0. Yeah, so this is the half width of this Gaussian, and this is the where actually the point is. Which is they note is critical for numerical stability. Please refer to the supplement for a detailed derivation. Great, because I didn't want to think about that too much right now. So we're gonna go there and see how do they found these equations exactly. But for now, I believe them that these are correct equations, of course, and we will see how they derive it. But what's good about these equations is that basically all of this you can compute very fast, right? Because it is just like just some algebra, and this TU and T delta is also, you can just compute from this difference, right? And T1 and T0 as basically your sampling points along this cone. So they are just basically saying where one cone ends and one cone starts. So you can all of this compute very fast. And the only thing that is different here from this values is this R. But this R also is, you can pre-compute it as here, right? Where is computation for R? Yeah, you just width of the pixel in world coordinates scaled by this number, right? So this is another very simple computation based on O and D. So these are our camera positions, right? So as long as we have the camera positions, we can like compute all of this very fast. And we can transform this Gaussian from the coordinate frame of the canonical frustum into a word coordinate. Yeah, so to do that, you just take this UT and you multiply it by D and add it to the camera position. So this is our basically our final position in the 3D space, and this is the variance of this 3D Gaussian in the 3D space. Yeah, makes sense. Okay, so this is our 3D Gaussian now positioned in the 3D space that we're gonna use. And then we derive the IPE, which is their actual thing that they put into the network, which is the expectation of a positionally encoded coordinate distribution according to aforementioned Gaussian. Okay, to accomplish this, it's helpful to first rewrite the PE in equation 1 as a Fourier feature. Yeah, so this thing. Yeah, this thing is rewritten as basically this multiplication here. So this is how you take all of the sine and cosines. Okay. Using the fact that the covariance of linear transformation of variables is linear transformation of the variable's covariance, we can identify the mean and covariance of our canonical frustum Gaussians after it has been lifted into PE basis P. Okay. Okay, computing the expectation over this lifted multivariate Gaussian modulated by the sine cosine position, these expectations have simple closed form expressions. Yeah, so this is the parameterization trick that parameterizes this Gaussian, and then what we do, we just multiply this U by the P basis, which is this, and we get the matrix for each dimension, and then we can just sine and cosine this and calculate the expectations for this matrix, right? Cool. What's next? We see that this expected sine or cosine is simply the sine or cosine of the mean attenuated by a Gaussian function of the variance. With this, we can compute our final epi feature as the expected sines and cosines of the mean and diagonal of the covariance matrix. Okay. Sine, expectation, diagonal matrix. Where denotes element-wise multiplication because positional encoding encodes each dimension independently. This expected encoding relies only on the marginal distribution of X and only diagonal of the covariance matrix. A vector of per dimension variance is needed because it's a sigma is prohibitively expensive to compute due to its relatively large size. To discretely compute diagonal matrix of the sigma, and this sigma is this part, right? Yeah. So they don't compute the whole thing, they just compute the diagonal because that's the covariance. That's the covariance that they need. Yes, because they treat all of these dimensions independently, so they don't need like an actual covariance between the features. They just need the variance in each of the dimensions, so they just need the diagonal features. Okay, that makes sense. Okay, so this is how they do it here. Okay, these vectors depend on just the diagonal of the 3D positions covariance, which can be computed as follows. So this is the variance in the t dimension. This is the variance in the perpendicular dimension. If these diagonals are computed directly, IP features are roughly as expensive as PE features to construct. Cool, let's say they are. With this, we can compute our final IP feature as expected size and cosine of the mean and diagonal of the covariance matrix. Let me think about this for a second more. Okay, makes sense. Now I understand. So we just compute the value for this sine and cosine, and we just use the diagonal because that's the variance of this matrix, and we can just compute it one by one as a vector to get it faster. And we compute for each value, we can compute with this equation, which is also looks very simple. So that's good. Okay. Figure 4 visualizes the difference between IP and conventional PE features in a toy 1 domain. IP features behave intuitively if a particular frequency in the positional encoding has a period that is larger than the width of the interval being used to construct the IP feature, then the encoding and the frequency is unaffected. But if the period is smaller than the interval, in which case the PE over the interval will oscillate repeatedly, then the encoding at that frequency is scaled down towards 0. In short, IP preserves frequencies that are constant over an interval and softly removes frequencies that vary over an interval, while PE preserves all frequencies up to some manually tuned hyperparameter L. By scaling each sine and cosine in this way, IP features are effectively anti-aliased positional encoding features that are smoothly encode the size and shape of the volume of the space. IP also effectively removes L as a hyperparameter. It can simply be set to an extremely large value and then never tuned. Okay, let's see the picture. It would help us understand it better. Where is the picture? Figure 4. Okay, let's see. Toy 1D visualization of the positional encoding PE used by NeRF and our integrated positional encoding IP right. Because NeRF samples points along each ray and encodes all frequencies equally, the high frequency PE features are aliased, which results in rendering artifacts. By integrating PE features over each interval, the high frequency dimension of IPE features shrink towards 0 when the period of the frequency is small compared to the size of the interval being integrated, resulting in anti-aliased features that implicitly encode the size and in higher dimensions and the shape of the interval. Okay, let's see. So NeRF, each point, we sample this point, we get the encoding, okay, for each dimension, and then we have encoded sample like that. Cool. Now here we have the encoding, and for this we have this like a whole interval, and depending on the size of the interval we have different features like that. So this is zeroed out, for example. This is just low values. Okay. Cool. So the idea is basically that because we do all of these transformations with the Gaussian, we eliminate some of the frequencies, and the frequencies that we eliminate are the higher frequencies, and they basically are eliminated if the Gaussian is small, right? If the period is smaller than the interval, in which case the P over the interval will oscillate repeatedly, then the encoding at that frequency is scaled down towards 0, yeah. Okay, that's cool. Aside from the cone tracing and IPA features, Mip-NeRF behaves similar to NeRF, as described in section 2.1. For each pixel being rendered instead of array, as in NeRF, a cone is cast. Instead of sampling n values for tk along the array, we sample n+1 values for tk. Computing IPA features for the interval spanning each adjacent pair of sampled point tk values as previously described. These IPE features are passed into an MLP to produce density and color. Rendering in Mip-NeRF follows equation 3. Recall that NeRF uses a hierarchical sampling. This was unnecessary in NeRF because its PE features meant that its MLPs were only able to learn a model of the scene for one single scale. But our cone casting and IP features allow us to explicitly encode scale into our input features and thereby enable an MLP to learn a multiscale representation of the scene. Mip-NeRF therefore uses a single MLP with parameters data, which we repeatedly query in hierarchical sampling strategy. So they do hierarchical sampling, but they have just one one MLP, because they can distinguish between whether the camera is close or not. This has multiple benefits. Model size is cut in half, renderings are more accurate, sampling is more efficient, and the overall algorithms become simpler. Our optimization problem is, as usual, because we have a single MLP, the coarse loss must be balanced against the fine loss, which is accomplished using a per parameter. We set lambda to 0.1 in all experiments, blah blah. Our coarse samples are produced with stratified sampling, and our fine samples are sampled from the resulting alpha compositing weights using inverse transform sampling. So this is exactly the same as in regular NeRF. Unlike NeRF, in which the fine MLP is given the sorted union of 64 coarse samples and 128 fine samples, in Mip-NeRF we simply sample 128 samples for the coarse model and 128 samples from the fine model, yielding the same number of total MLP evaluations as in NeRF for fair comparison. Before sampling TF, we modify the weights W slightly. We filter W with a 2-tab max filter followed by a 2-tab blur filter, which produces a wide and smooth upper envelope on W. A hyperparameter alpha is added to that envelope before it is normalized to sum to 1, which ensures that some samplers are drawn even in empty regions of space. We set alpha to 0.01 in all experiments, okay? Mip-NeRF is implemented on top of JAX-NeRF, for implementation of NeRF, blah blah. Blah blah, train faster than TensorFlow implementation, blah blah. Nothing interesting here. Batch size of 4096. Learning rate. Okay, cool. So the main idea here is this this Gaussian reparametrization and this trick that we just have to compute the diagonal diagonal vector of this covariance matrix, so basically the variance in each dimension, and that is enough to compute the expected value for particular cone depending on the x, right? So that's great. And we get this result where we just basically have different frequency encoding depending on the size of the interval and how big the Gaussians in the interval is, which is very cool. Okay, let's go further. So the results, they evaluate the Mip-NeRF on many things. Is there something interesting? They trained on TPU v2 with 32 cores, so one single TPU. They have another benchmark. Blah blah blah. These are visualizations. Very cool. They construct this new dataset. It's called Multiscale Blender dataset. Dataset was constructed by taking each image in the Blender dataset box, downsampling it a factor of 2, 4, and 8, and modifying the camera and tracing accordingly, and combining the original images and 3 downsampled images into a single dataset. This way they get multi-resolution dataset. Due to the nature of projective geometry, this is similar to re-rendering the original dataset where the distance to the camera has been increased by scale factors of 2, 4, and 8. This makes sense. When training Mip-NeRF on this set, we scale the loss of each pixel by the area of the pixel's footprint in the original image. Okay. The loss for pixels from the 1/4 image is scaled by 16, etc. So that the few low-resolution pixels have comparable influence to the many high-resolution pixels. Okay, makes sense. The average error metric for this task uses the arithmetic mean of square error metrics across all 4 scales. That's as usual. Okay, anything interesting here? Blah blah. Okay, cool. It's very cool. Let's see the picture 6. Even on the less challenging single-scale Blender dataset, Mip-NeRF significantly outperforms NeRF and our improved version of NeRF pay particularly on small or thin objects such as the hulls of the Lego truck and the ropes of the ship. So this is ground truth, this is NeRF with these breakings here and here. This is the improved version and this is Mip-NeRF, and we can see this is much better and closer to the ground truth, that's why it was the state of the art at that time. Okay, cool. They also tested against this super sampling approach. Cool. We have presented Mip-NeRF, a multiscale like model that addresses inherent aliasing of NeRF. NeRF works by casting rays and calling the position of points along these rays and training separate neural networks at distinct scales. In contrast, Mip-NeRF encodes the positions and size of canonical frustum and trains single neural network that models the scene at multiple scales. By reasoning explicitly about sampling and scale, Mip-NeRF is able to reduce error rates relatively to NeRF by 60% on our own multiscale dataset and by 17% on NeRF's single-scale dataset, while also being 7% faster than NeRF. Blah blah. We hope that general techniques presented here will be valuable to other researchers working to improve the performance of ray tracing based on rendering models, which it was. Awesome. Let's go look at the particular derivations, because that's the interesting part, I think, here. The results are great, but let's read the derivation and see how it works. Okay. So let's go first look at canonical frustum integral derivations. Okay, that might be helpful to understand all of these equations here. In order to derive formulas for the various moments of the uniform distribution over a canonical frustum, we consider an axis-aligned cone parametrization. Okay, this is how you parameterize the cone in a standard way. This changes variables from Cartesian space gives us differential term. Okay, so the dx dy dz determinant. We calculate the actual new coordinates in this frustum space. That's usual. The volume of the canonical frustum, which serves as the normalizing constant for the uniform distribution, is that. So we just calculate the volume of this cut of the 3D shape. We get that. Yes, the probability density function for the points uniformly sampled from the canonical frustum is the size divided by the volume, and we just have to calculate the first moment of this. So this is t times whatever equation we have. We just divided by the space. We get expected value of that. So they integrate and they get these equations that they use later. And then the moments of x and y are both 0 by symmetry. Yes, and the second moment of t is, so we need to have variance, so we just do t squared here instead, and we get that. And the second moment of x is, we go for the x parameterization, so this is here, yeah, and then we go for the, we get that, and the second one of y is the same by symmetry, of course, and all cross terms in the covariance are z, also by symmetry. With these moments defined, we can construct the mean and covariance for a random point within our canonical frustum. The mean along the ray direction ut is simply the first moment with respect to t. The mean along the ray direction ut is simply the first moment with respect to t. Yes, that's true. the variance of the canonical frustum with respect to T follows from the definition of variance, of course. The variance of canonical frustum with respect to its radius R is equal to variance of frustum with respect to X or by symmetry Y. Okay, makes sense. Since the first moment with respect to X is 0, the variance is equal to the second moment. Yes. Computing all three of these quantities in their given form is numerically unstable. The ratio of the differences between T1 and T0 rises to large powers. Is difficult to compute accurately when T0 and T1 are near each other, which is the case for us because we have a lot of these cuts in the 3D cone. Yeah, using these quantities in practice often produces 0 or none instead of accurate values, so this will be 0 and everywhere is 0, so that's not good. And we therefore reparameterize these equations as functions of the center and spread of T0, so this and T1, so this is the center, this is the spread. This allows us to rewrite each mean and variance as the first order term that is then corrected by higher order terms, which are scaled by T delta. This gives us stable and accurate values when T delta is small. Our parameterization values are, so mu T is T mu this variance. Okay, let's compare that very quick. Okay, so a lot of algebra here to get there, but that's reasonable. And then here you just do that inside. Makes sense. Okay, let's see further. Note that our multivariate Gaussian approximation of a canonical frustum will be inaccurate if there is a significant difference between the base and top radii of the frustum, of course, because we don't have a ball, we have a trapezoid in the cut, right? So this will be true for frustums that are very near the camera's center of projection when the camera FOV is large. This is highly uncommon in most datasets, but may be an issue if one were to use Mip-NeRF in unusual circumstances such as macro photography with fisheye lens. Yeah, so this would be an issue if you have very fast, you have small length from the ray, and then at the beginning you have like a small circle, and then you get like a very big circle for a small D. That would break the thing, because we will just have a ball here and we should have like a more like a 3D shape, like a cone-like shape. So that's a big thing, but like for us it works. So that's cool. Now they discuss the L hyperparameter, so let's see what they do here. IP features can be viewed as a generalization of PE features, okay? Or more rigorously, PE features can be thought of as hard IP features in which all points are assumed to have identical isotropic covariance metrics whose variance has been heuristically determined by the L hyperparameter. The value of L determines the frequency at which PE features are truncated, just as the Gaussian function of variance in IP serves as a soft truncation of IP features. Because the soft maximum frequency of IP features is determined entirely by geometry and intrinsics of camera, IP features do not depend on the L hyperparameter, so using IP features removes the need for tuning L. This is because in PE, the L parameter determines where the high frequencies in the PE are truncated, but in IP, these frequencies are naturally attenuated by the size of multivariate Gaussians used as an input to the encoding. The smaller the Gaussian, the more high frequencies will be retained. To demonstrate this, we perform a sweep of L in both Mip-NeRF and NeRF and report the test set PSNR for single sin, which is visualized in figure 7. And we see that in NeRF there is a large values of for L in which performance is maximized, but values that are too large or too small will hurt performance. But in Mip-NeRF, we see that L can be set to an arbitrarily large value and performance is unaffected. In practice, in all Mip-NeRF experiments in the paper, we set L equals 16, which is value that results in the last dimension of IP features constructed during training to be less than numerical epsilon. Yeah. So basically what they say here is that L, if you have like L features, you just have just set the boundary that, okay, we only care about L features exactly, no matter where we sample the point. What the Gaussian representation they have is doing is basically determining how big the Gaussian is, and how big the Gaussian is comes from where is the cone compared to the camera. Is it close? Is it far? And based on that, calculate and how is this impacting the pixel, and how big the cone is, the more frequencies are there, right? So the smaller Gaussian, the more high frequencies we have, and if the cone is big, that means we have low frequency features because there is a lot of space for this pixel, so we don't need that much high frequency details. So then we decrease the frequency, we limit frequency earlier, and if we do that, limiting the frequency earlier is basically make the whole thing much slower. Yeah, no much slower, much if we limit the high frequency details earlier, we basically tell the model that there is like less, that the information is more diffuse in the space, and because of that it can determine that this is different compared to if we had like a set like 16 features that would be the same as if the information was close to the camera, and it would encode the high frequency details that are not there, not represented there. So that's how this differentiates between these two approaches, right? And because we use Gaussian specifically, we have this like a soft truncation. We don't have like a boundary, so we don't have like a cut, and we say, oh, for this kind of point you should have 5 features or 7, right, or 3. We instead have this like a Gaussian that allows us to recalculate how much we should put emphasis on each frequency detail, and basically if it's like above some level, we basically just have zeros there, right? We don't have values there. So that's how it looks here. Let's see further. Blah blah blah. This is hyperparameter, so I don't think we should have to care about it that much. Forward-facing scenes, activation function, model details, optimization, super sampling baseline, view-dependent effects. We handle view directions exactly as done in NeRF. The ray direction day is normalized, positional, encoded with L4 and injected into the last layer of MLP after T is predicted but before C is predicted. This is omitted from our notation in the my paper for simplicity's sake. So we see that the only thing that they are using this for, like they are using the first encoding for the general positional encoding, but they don't use it for the for this camera view dependent theta and phi. So these are as usual trained with L equals 4. So interestingly, they don't use this representation for the view dependent effects, and that's weird for me, because it would feel to me that the view dependent effects are also scale dependent, but yeah, they are not using that here for some reason. Interesting. Okay, what's next? And they have alternative Gaussian positional encodings versions of this. Okay. More results. Okay, cool. So that will be it for now, I think. Thank you so much for watching. It was quite a long stream, but yeah, we will be finishing here, I think. And the next time we will be going into Mip-NeRF 360 and seeing how they change this baseline to allow for unbounded scene regions. Yeah, that's it for today. So thank you so much.